Philip, and today I'll be discussing Riemann sum. So our outline starts out today with describing what Riemann sum is, and next is going through an example in order to understand how Riemann sum works. So first, what are Riemann sum? So Riemann sum is a form of approximation of an area, and this area is not of regular shape. So what do I mean by that? So to further help you visualize on how Riemann sum works or what it is, so we'll go by with an example. So here we have a function. Draw the y-axis there and the x-axis here, x and y, and say we have our function here. This is our function f of x. Let's say our function here is x squared plus 1. But this is just for example purposes. I know if you Google what that function x squared plus 1 is graph, like how that graph looks like, it does not look like this. And let's say that you want to find out the area between that bound by that function and the x-axis in the domain of x equals 1 to x equals 4. So we have 2 and 3 here. So how does Riemann sum work? Riemann sum works in trying to find out the answer of what is the approximate value of this area, because unlike a rectangle where your area is basically length times width, you can't definitively give a good approximate of this area because of this curve here, making it an irregular shape. Let's remove that. So the first step in trying to apply Riemann sum is determining the area, the kind of shape you want to divide your irregular area into. So this shape is determined by, usually it's in your preference on what shape you want to compute your area by. So it could be you trying to form as many triangles into this area that you're looking for, or fit as many circles, or fit as many rectangles. And for our case, and in most cases, you'd see explanations using rectangles because of how simple it is to find the area of a rectangle, wherein you just need 2 dimensions and it's just length times width. So there, we're gonna try to fit as many rectangles as we can in this area right here in order to approximate our area for that irregular shape. So the first step is to divide your your domain here of 1 to 4 into equal intervals. So for our example, we'll select an equal interval of 1. So here, as you can see, there are 3 ones between 1 to 4. So we'll be dividing that into 3 rectangles. So here, let me highlight that. So that's the width of the first rectangle, that's the width of the second rectangle, and that's the width of the third rectangle. Next is the height. So now that we have our width, how do we determine the length or height of our rectangles in approximating this area? So our height is, actually it depends on the preference of the person solving, on whether you would like to use this left side equivalent of the function as your reference for your height, or the right side of your rectangle as your reference for your height. So what do I mean by that? I mean that your height for your first rectangle could either be f of 1 or f of 2. But in your selection, you have to be consistent. So if I select f of 1 to be the height of my first rectangle, for my second rectangle with this base right here, I'll have to select f of 2, which is corresponding to the left side of that rectangle, the left height, as I would say. And for the third rectangle, which is with this base, with this width, your height has to correspond to f of 3, since that is the left height of this third rectangle. So if you choose the right one, the right height as your reference for all of your rectangles, so for your first rectangle, it would be f of 2. For your second rectangle, it would be f of 3. And for your third rectangle, it would be f of 4, would be your height. But for our case here, let me undo that to avoid confusion later on. We'll use the left side as our reference height. Left side of our rectangle. So the left heights. So the left height of our first rectangle is f of 1. So let me draw that whole rectangle here. So it goes above the curve, since the curve goes down here, but your f of 1 is still higher than that whole portion. Then your second rectangle, f of 2, which is this one, there, connect that height, and f of 3, which is quite close to f of 2 in this drawing, but let's give it a bit of a difference just to distinguish it. F of 3. This height is f of 3. So there, you have your first rectangle, your second rectangle, and your third rectangle right there. So in order to approximate the area that we were looking for, which I will highlight just so that we don't forget, this area, this is the area we're trying to approximate. And you have 3 rectangles. We'll solve for the areas of each of our 3 rectangles and then add them up in order to get our approximate. So first step, first rectangle, let's do this step by step. First rectangle. So that the height of that first rectangle is f of 1 times, what is our width? Our width is 1, as so for all of our rectangles. So for our second rectangle, our area is f of 2, which is our height for the second rectangle seen here, f of 2, times 1, which is our width. Then for our third rectangle, it's f of 3 times 1. So f of 1, the value of f of 1 is substituting x, making x equals 1 in our function here of x squared plus 1. So that would be equivalent to 2 times 1 for this. That would be equal to 2 basically. Then for the second rectangle, f of 2, substitute x equals 2 in x squared plus 1. That's 4. 4 plus 1, that's 5. Times 1, that's equal to 5. And for the third one, f of 3, substitute 3 into this function. That's 9 plus 1 was 10. So you get there 10 times 1. So 10 is your area for the third rectangle. So now that you have the individual areas of your rectangles for your first, second, and third rectangle, you add them up for your approximate areas. Our approximate area. So it will be 2 plus 5 plus 10, which will be equal to 17 square units, since it's area 17 right there. And that is your Riemann sum basically. So Riemann sum is a form of approximation using known sums. So, or in other words, other definitions might say finite sums. This is used in solving for integrals, or a foundation in how you solve integrals as we further discuss calculus in the future.